The discontinuities of a function are of three types. Let's begin with the definition. In this definition, I'm going to restrict myself to functions defined on an open set just for convenience. Let f from a b to r be a function. Let x be in a b be such that f is not continuous at x. We say, number one, x is a removable singularity if limit y tending to x f of x exists but is not equal to f of x. That means the limit values exist. Just a second, I will not call it a removable singularity, I will call it a removable discontinuity. I want to reserve the term singularity for more pathological things later in the course. So x is a removable discontinuity if limit y going to x f of x exists but is not equal to f of x. Why is this called a removable discontinuity? Well, it's obvious why it is called a removable discontinuity. What you do is, if we define f of x, if we redefine f of x to be this limit value, limit y going to x f of x, then obviously you end up with a continuous function. So in some sense, this function f has a fake singularity at the fake discontinuity at the point x. It's not really discontinuous at the point x. The way that function has been defined at the point x is what is making it discontinuous. So redefining that function at just that one point is going to fix the issue. So that's why this is called a removable discontinuity. Number two, x is said to be a jump discontinuity, if limit y going to x minus f of y, comma limit y going to x plus f of y both exist but are not equal. Well, again, the terminology is very explanatory. When you approach from the left and when you approach from the right, both limits exist but they are not equal. So there is a jump happening at the point x. Okay, so again the terminology is very nice. 3. So two cases of mathematicians having vivid and nice terminology means that the third terminology is going to be ridiculously bad. If neither 1 or 2 is satisfied, then x is said to be an essential discontinuity of f. So I think the idea behind it is the situation is bad. There is nothing really you can do about the discontinuity if it's neither the removable discontinuity or it's a jump discontinuity. Therefore, you just say it's an essential singularity. There's nothing you can do about it. So I don't know what really motivated this terminology here. Okay, so these are the three types of discontinuities that can happen. Let's draw pictures to illustrate these rather than give actual real examples because they're rather easy to actually give. So suppose you had a function that is 0 on the negative real line, 0 on the positive real line, but for some reason it's 1. It's 1 at the point 0, then clearly this is a removable singularity. You just have to redefine f of 0 to be 0 to make that discontinuity go away. The second is a jump discontinuity. Well, that's the famous Heaviside function. You can just take, I'll just take it to be 0 on the negative real axis and 1 on the positive real axis. This point I can define it whatever I want. It's still going to be a jump discontinuity. What is essentially happening is that the left hand limit is 0, whereas the right hand limit is 1. Okay. And for the third example of an essential discontinuity, we have the very famous example, which is my greatest enemy to showcase my poor drawing skills. It's this function. Take sine 1 by x. Okay. Of course, I have to draw it for the negative. I'm not going to embarrass myself twice, so I'm not even drawing it on the negative x-axis. Sine 1 by x when x is not 0, and let's just say 0 when x is 0. Okay. This function certainly has a discontinuity at the point 0. Neither the left hand limit nor the right hand limit actually exist at the point 0. Therefore, this is an essential singularity. Okay. Now, I'm going to prove a very interesting theorem about the singularities of a monotone function. Recall, a monotone function is one that's either increasing or decreasing. I will just state it for the increasing case. It's similar for the decreasing case. Exact same proof will work with slight modifications. Suppose f from AB to R is an increasing function. That is, if you don't recall the definition, if x is less than y, f of x is less than or equal to f of y for all xy in the closed interval AB. Okay. Suppose you have an increasing function. Then the discontinuities of f are all jump discontinuities. They're all jump discontinuities. Moreover, the set of discontinuities, that is, you put all the points of discontinuities into a set. The set of discontinuities is a countable set. So monotone functions are going to be continuous at almost all the points of closed interval AB. Whenever there is a discontinuity, it's going to be a jump discontinuity. Okay. So proof. Okay. Now let x be in AB. Be a point of discontinuity. Now, since I have defined discontinuities only for open intervals, what I am going to do is, for ultra precision, I am going to restrict f to the open interval AB. Okay. So that because I have not really defined what the meaning of discontinuities at these endpoints are. So for precision, I am going to just restrict the function f to this open interval AB. So let's take a point x in AB be a point of discontinuity. We have to somehow show that it's a jump discontinuity. Well, how do we do that? What we are going to do is, let us take xn in AB, xn converging to x, xn is less than x and increasing. Okay. In fact, I'm going to demand that it's strictly increasing. really doesn't make a difference, but I can demand of xn whatever I want. So what I'm going to do is, so I have this function. I'm going to draw the discontinuity as a jump discontinuity because that's what it's going to be. I have this increasing function. I am focusing on this point x. What I'm doing is I'm taking a sequence xn that is converging to this point x. Okay, so this sine curve type thing I've drawn is just a doodle. It really has no place here. So I have this sequence xn which is converging to x. Okay, and xn is strictly increasing and xn's are all less than x. Okay, how does this help? Well, observe that the sequence f of xn is increasing. We can't say that it's strictly increasing because all I've assumed is that the function f is increasing. I've not assumed that the function f is strictly increasing. I've just assumed that if x is less than y, f of x is less than or equal to f of y. So observe that the sequence f of xn is increasing and it is bounded above by f of x, right? Because the function f is an increasing function, so the sequence f of xn is bounded above by f of x. This means that f of xn converges to some y. Why? This is the monotone convergence theorem. If you have an increasing sequence that is bounded above, then it is convergent. Now this y need not be equal to f of x. There is no reason on earth why this y should be equal to f of x. I'm not going to claim that at all. All I know is that f of xn converges to y. Okay. Now I claim that this will force limit x going to not x going to y. I have to use a new variable, z going to x minus f of x has got to be equal to y. This is the claim. Okay. Now I'm going to leave it to you to go back to the definition of one-sided limits and check that the argument I'm about to give is 100% proper. So what we do is the following. Take another sequence un converging to x, un not equal to x, un less than x. Okay, actually un less than x will cover the case un not equal to x. I'm just emphasizing uns are never equal to x. So I'm just going to take any sequence un converging to x from the left. If I can show that f of un converges to converges to just y, then we are done. Essentially what I'm doing is no matter what sequence you choose that converges to x but from the left, then the image sequence must converge to y. Then the limit z going to x minus f of x equal to y is true. Okay, so this is what I wanted to check from the definition of one-sided limit. It's just 2 or 3 lines of verification. Okay, why is this the case? Well, think about what is happening. We have this point x and we have this sequence xn. Okay, now because un converges to x, given any epsilon greater than 0, we can find xn such that, or rather we can find capital N such that two things happen. First of all, f of x, not f of x, modulus of y minus f of x capital N is less than epsilon. Well, we can certainly do this simply because f of xn converges to y. Okay. Second is if small n is greater than capital N, un is greater than x capital N. This requires maybe 30 seconds of thought. Well, think about what is happening. Xn is somewhere over here. What I'm claiming is if you choose n, okay, so this I really cannot do. We can find n comma m. We can find n comma m. I got a little bit too ambitious. So if small n is greater than capital M, then un is greater than x capital N. This is what I want. This is what I want. Well, why can I guarantee this? Because un converges to x. Because un converges to x, there is a suitably large capital M such that if small n is greater than capital M, then un must lie in this interval, right? So there is some finite distance. There is some finite distance between xn and x. Call that distance delta. All I'm saying is for this delta, there is a corresponding n delta, which I'm just calling capital M. Okay. So this just requires a little bit of thought. All I'm doing is since un converges to x, I can force it to be greater than x capital N for suitably large small n. That's what I have written down. Okay. Now how does this help? But we actually have more data than what I have written down. We in fact have, I have written modulus of y minus fxn. I could have forgotten about the modulus. We actually have f of xn is less than or equal to y, right? And in fact we have f of xn is less than or equal to f of un is less than or equal to y. Okay, for n greater than capital M. Okay, in other words, y minus f of un is also less than epsilon. There's no need to put the modulus because we know that f of un is less than or equal to y. Okay, which shows un converges, not un, f of un converges to y. Okay, so the claim is proved. So the left-hand limit of the function f exists at the point x. Okay. Now similarly, right-hand limit exists at the point x. Okay. Now I'm going to end this proof by giving you a very easy exercise. Show that x cannot be a removable singularity. Cannot be a removable discontinuity. I keep using the word singularity. That's because I'm a complex analyst. So if you learn complex analysis, you will understand why I keep saying removable singularity. I apologize in advance. So if I say singularity, I am entrusting you with the task of interpreting it as discontinuity. Okay. Show that x cannot be a removable discontinuity. That will complete the proof. That means left-hand limit exists, right-hand limit exists, but they are not equal. Okay. So since the right hand limit and the left hand limit exists, if the right in fact, let me just rephrase this exercise in a slightly more palatable form. Show that it cannot happen that right hand limit is equal to left hand limit. Okay, this is a better way of phrasing this exercise. Show that it cannot happen that the right hand limit is equal to the left hand limit. Hint, x is a discontinuity. Remember that x is a discontinuity. So I'm just phrasing the exercise in a slightly different form, which is, I think, more clear. So left hand limit exists, right hand limit exists, and I'm leaving you to show that left hand limit cannot be equal to the right hand limit. Okay. Now, this concludes the proof. In fact, this concludes the proof. At least the proof of the first part, that all the singularities are jump discontinuities. All the discontinuities are jump discontinuities. So now the second part is this fact that the set D of discontinuities is countable. Now this proof requires this machinery of oscillation, right? What you do is the following. Look at dk defined to be x in AB such that oscillation at x of f is greater than or equal to 1 by k. Okay. At a point of discontinuity, by an exercise that I have given, I must add an easy exercise that I have given, you can show that the oscillation will have to be non-zero. Okay, and in fact it has to be a positive quantity just by the way the oscillation is defined. So look at those points where the oscillation is at least 1 by k. Then union over dk is going to be equal to d. Okay, union over dk is going to be d. Now observe, if we can show that each dk is finite, then we are done. Because a countable union of finite sets is certainly countable. Then we are done. Okay, so fix k. We are going to focus our attention on dk. Okay, now note that each discontinuity x in dk is a jump discontinuity. Fine. Moreover, limit x going to c minus of f of not x going to c minus y going to x minus f of y, limit y going to x plus f of y minus this has got to be greater than or equal to 1 by k. Right? This is because, check. I will just write this is because the oscillation at the point x is at least 1 over k. Because the function is having an oscillation at least 1 by k at the point x, it has to be the case that the right hand limit minus the left hand limit must also be at least 1 by k. One of the crucial things to understand why this must be the case is to also observe that, let's see, where is the graph? F of x has to be somewhere in between these two, in between this jump. Okay, the value of f of x has to be in between this jump because the function is an increasing function. It cannot be here, it cannot be here. So essentially f of x is going to be sandwiched between the jump, and this jump has to be at least 1 by k because the oscillation at that point is 1 by k, and f of x is not going to contribute that much oscillation. Okay. Now choose a number, let's say capital N, so large that capital N by k is strictly greater than f of b minus f of a. This is always possible because f of b minus f of a is going to be a finite quantity. If dk has more than capital N points, that means there are at least n places where the jump is at least 1 by k, then it is trivial to check. That f of b is going to be greater than or equal to f of a plus, in fact not greater than or equal to, in fact strictly greater than, it's going to be strictly greater than f of a plus n by k. So what is essentially happening is you start at f of a, each time you encounter a jump, you're going to increase the value by at least 1 by k, and this is, since this is a monotone function, it's an increasing function, you're going to preserve at that level at least, and you're going to jump again at 1 by k when you encounter the next discontinuity, and this is going to happen at least capital N times. So f of b has to be greater than f of a by n by plus n by k, a contradiction, right? So because at each jump there's a jump of 1 by k happening, there cannot be too many jumps. So dk is a finite set. And the net upshot is union of dk is countable. Okay. So this concludes the proof. There's a very nice idea in this proof where we use the oscillations to capture how much the functions jump and limit the number of such jumps because it cannot jump to exceed f of b. This is a course on real analysis, and you have just watched the module on classification of discontinuities and monotone functions.